today is talking about designing of RC slab, one-way slab. When we say RC slab, we mean it's a plate supported by beam slabs or columns, which is, there are types of slabs, of course. We have two-way slab, one-way slab, but when we talk about, today we're going to talk about only one-way slab. And talking about one-way slab is that the width, which is B, and the length, so that the length and the width ratio to the width is 2 or more. When the length to width ratio is more than 2 or 2 or more, that means it is one-way slab. And when we say one-way slab, that means the direction of the load is one direction, which is to the short direction, this direction of the load. And then this slab will bend like that, supported here, supported there. Okay, so this is an important aspect of understanding the one-way slab and what does it mean. So it bends in the short direction. It bends in the short direction. All right, so when we talk about one-way slab, again, we have, of course, guidelines from the ACI code. We have ratios that we need to understand, and all of these. Actually, designing one-way slab is like designing a rectangular beam, but it has a really large width to depth ratio. Width to depth is really huge. It's just designing as a beam, but that's the only difference. Okay, so how do we start? We start by taking a strip in the slab. We'll take a strip in the slab. This strip is either 1 meter or in US customary, we say 1 feet. Okay, so you take a strip in the slab, right? Like, for example, here, you take a strip like that. This is one meter or 1 foot, and we take it aside and we start designing. And then after that, when we design it, we generalize it on the whole slab. So everything that we will work on will be, for example, inch per foot, always. Per foot, I mean per the strip, or meter, when we say millimeter, in SI custom per meters. Okay, doing it quickly. So the rest, in other words, we're designing, for example, a series of beams. So in other words, we're designing a series of beams that has a width B. So it's like a beam next to a beam next to a beam. It's like that. And every beam is 12 inch or 1 foot, as I said, or 1 meter strips. Okay, starting with this. Actually, just to understand, always engineers should ask why. Why do we do that? Because the load of 1 foot unit equals the load on the whole slab. We should know that the main reinforcement, of course, for the flexure is placed along the long direction as well. So for example here, let's starting talking about the main reinforcement and ACI code. So the first aspect is about the deflection. If the slab was simply supported, it has minimum requirement by ACI code for the deflection. So we're talking about one-way slab, which is here, length over 20. Depends on the situations that we explained last lecture, or it's about designing of rectangular beams. This is from ACI. There are spacing requirements from the ACI for main reinforcement and for shrinkage and temperature reinforcement. In slabs, we have two types of reinforcement. We have main one, which is the one that's taking the load, main rebar or reinforcement, and the other one is shrinkage and temperature. Okay, talking about the main reinforcement, the area of steel is actually calculated by the area of the bar divided by spacing, but multiplied by 1 foot, which is 12 inch. Everything will be clear when you start designing or start calculating. Quickly saying, so the ACI recommends that the spacing between the main bars should be either 3h, 3 multiplies the depth of the beam, the whole thickness of the beam, or it shouldn't be more than 18 inch. Okay, these are the spacing of the bars, these spacing, all right? Okay, talking about the other types of rebar, which is the one that is called temperature and shrinkage. Actually, this is for understanding why it is there. It is actually, we use it to hold the main reinforcement tightly. We're gonna see it in a 3D in the next slide. And as concrete actually harden, it shrinks, because of difference in temperature, winter and summer. So it shrinks and expands due to the temperature stresses. Okay. And what does that mean? The code states that the shrinkage and temperature reinforcement must be added to reduce the stresses induced by the shrinkage and temperature due to the weather changes. And it's actually has, we'll talk about two criteria. Talk about first the spacing. The spacing is also either 5 multiplied by h or also 18 inch. Okay, this is the maximum spacing. And the minimum spacing, or the minimum reinforcement that we have to use, minimum reinforcement is depending on the Fy, which is the grade of steel. If Fy was 40 or 50 KSI, that means the minimum reinforcement we're gonna use is 0.002 BH. If it was more, which is Fy is 60 KSI, kilo pound square inch, that means we're gonna use 0.0018 BH, which is actually equivalent to the one, if you're gonna use metric, this is equivalent to 30 to 300 to 350 megapascal if we're talking about an SI, and this is equivalent to 420 megapascal. If you're gonna talk about more than 420, that means it will be, you have to refer to the code. There are equations how to deal with it, but mainly, designers choose this most of the time. Okay, so we talked about why do we need shrinkage and temperature. We talked about the main reinforcement. Now the last step is talking about the clear cover. So there is the cover that we have to choose. The slab is different from the beam. It's actually, the code calls for 3/4 inch, or what we say, 20 mm, 2 cm. This is called the clear cover, and we're gonna see what's the clear cover because it's different from the cover. The clear cover. Actually, you can say the clear cover is the cover that minus the diameter of the bar. I'm gonna see it now in an example that I'm gonna solve. Everything will be clear, don't worry about it. Okay, so let's move to the next slide. Let's assume that we have a slab that is 10 foot in span. Okay, we have a life load, let's write it here. We have life load of 200 pound square foot, and let's take the normal FC prime that we usually take, which is 3000 psi, and Fy is 60 psi. So we need to design a slab that spans 10 foot. Okay, and let's see how do you do that. Let's start with actually in the previous slide I have presented a table for deflection that will give me quickly a quick decision. How to start. So h, which is the depth of the slab, is actually length divided by, if it is simply supported, this is simply supported, divided by 20. This is the minimum the minimum requirement for the deflection. Since the length is in foot, I have to change it into inch. So 12 multiplied by 10 for unit conversion, divided by 20. This will give me 6 inch. 6 inch is actually 15 centimeter. That's the nominal or the usual, slab thickness, 15, 16, 17, 18. Anyway, so then we'll go and calculate the D. D is the effective depth, which is the depth of the beam, depth of the slab minus the cover, but also minus the bar diameter, which is half of the bar diameter. Okay, Mr. Anas, we didn't understand what is that. Why did you add this? Fine. I will understand it. I will explain it here. This is the beam, or sorry, this is the slab. The width of the slab is 12 inch or 1 foot because it's a strip. This is 6 inch, right? D, we all know, let's assume there's a rebar here for now, 3 rebars. D is from the middle of the bar till here, right? That's D. This is what we are calculating. So it is the clear cover, which is from here to here till the end of the bar, right? This is the clear cover, which is 3/4, as I said. Also, we have to take half of the bar diameter, but we don't know what's the bar diameter. We didn't even design it, Mr. Anas. So what do we have to do? Actually, we have to assume. Let's assume, usually for the slabs, we use bar number 4 and bar number actually 5. 3, 4, 5 actually. Right. So bar number 4 from here is actually 1/2 inch. Right. So that will give me D is equal to H, which is 6, minus cover is 3/4 inch, minus 0.5, half of the bar diameter, but the bar diameter is also 0.5. And then eventually we will have D. Actually, this assumption should be made professionally. So I mean by that, engineers have a decision from the experience that it is bar number 4, number 5. In the Gulf, actually, we use in the metric unit, so usually we use T12, which is 12 mm diameter. Okay, actually, now bar number 4 is equivalent to T12. So this will give me D, which is 5 inch. So I get D, I get H, and B is 12 because it's a strip. So now what? Now we have to calculate the moment. In order to calculate the moment, I need the on weight. On weight of the beam is so it's 6 divided by 12 for unit conversion. 6 is H multiplied by B, but B is 1 foot, so it's ignored. Multiplied by 150, which is the unit weight of concrete for the normal concrete. This will give me 75 pound square foot for the strip. Again, don't forget that. Okay, so and then this will give me the ultimate load. This is 1.2 dead plus 1.6 times live. This will give me 410, or let's compute it in kilo pound. So 0.410 kilo pound square foot. Okay, I should write KSP. Okay, then the moment for simply supported is what? Moment is WL square over 8 from structure. So this will give me 5.125 K-foot. Okay, I got the moment. Now from the previous slides, and I keep saying about the moment equation, where we say phi mn is equal to mu, which is equal to phi, which is 0.9. What's that, man? Phi 0.9 multiplied by rho, which is unknown, the percentage of steel, multiplied by B, which is 1 foot, multiplied by D square. I mean, 1 foot is just, you put it as 12. We're working in inch. Multiplied by D square, right? Multiplied by Fy, which is 60. And this will be multiplied by 1 minus rho Fy divided by 1.7 Fc prime. Everything is known except rho. If you do the math, guys, you will get rho as 0.00393. If you compare it with rho minimum and rho maximum, we know that from the previous also presentations that rho minimum will be 0.00333 and rho maximum is 0.0181. So our rho fits between these two, so we are in tension control, right? Perfect, everything is okay. Now we need to go and check our area of steel. How much AS? So AS is what? Rho BD, and it is equivalent to 0.00393 multiplied by B multiplied by D, and this will give me 0.236 inch square per foot per the strip again. Right, I have to choose a rebar that fits with this. We have this table here that gives us, I choose number 4 from the beginning, so I have to look here. Number 4, where is something close to 0.23? And the closest thing is choosing the bar number 10. Right, this will give me 0.24. So I'm gonna say choose diameter 4, which is the one I use, at 10 inch. So the bars will be for number 4 bars will be placed every 10 inch. Okay, so AS again is actually 0.24. Do I have to again check and the demand? I mean, fireman, if it is really equal, then is fireman greater than MU? Yes, it is greater than, without even checking it, because we chose area of steel higher than the one we did, and our assumption was perfect, so we don't really need to go and check it again. So our design is safe. Okay, so this is the main steel, guys. This is the main steel. So we have to check the spacing. Is the spacing less than 18 inch? Yes. So S, which is this one, which is 10, is less than 18. So we're working as per the code. Now I have to calculate the shrinkage and temperature steel. ASS, let's call it, which is shrinkage and temperature, is 0.0018 BH, because FY is 60, right? This is why I chose this. And this will give me 0.129 inches square per foot. Again, going to the same table, I want something that gives me 0.129. I don't have to stick to number 4, because that was my assumption for the main steel. For the shrinkage temperature, I just need to check for a lighter bar, because the bigger bar or the main bar will be for the main reinforcement. So 0.13 is the, I think, closest one to this. Yes, so we're gonna use AS or SS, we said 0.13. Choose bar 3 at 10 inch. Again, checking the spacing is less than 18 inch, which is this one. So we're working as per the code. Right, we finished designing. So what does that mean? That means I'm gonna take you to the next slide, showing you. I want to show you guys what does that mean, how the one-way slab reinforcement works. Okay, so this is it. So what we are talking about here, what I'm showing you here, something that is really important. So my main bars are placed per strip, which is, in my case, diameter number 4 at 10 inch, right? And the temperature and shrinkage, which are the minor bars, we chose it to be number 3 at also 10 inch. So here the bars are tied together, right? And you can see the main reinforcement, which is this one, is along the short direction, because once the slab is loaded, the slab will bend like that. Sorry, what's that, man? This is the bending way. So we need the main reinforcement to be like that. And the shrinkage, we said, why do we need the shrinkage? This is it. Hope you enjoyed it. Thank you so much for watching.